All right. So this slideshow is going to show us what units that we use for gas laws, and also the units that we be using a lot for chemistry. So this is a good place to give you an idea about the units, uh, because we'll have numbers. Like say I have 10 particles and I change it to 20. And what happens to volume? If it goes doubles, but you want to know what units they change. The units that we'll be using in gas laws at the macro level are volume, pressure, temperature, and amount. All right. Volume, typically liters. Okay, we'll go more over that. Milliliters, anything that's cubed. Inches cubed, because volume is technically length times width times volume. Times length times width times height. So cubed, okay, inches cubed, yards cubes, etc. You may have heard cc's, which is the same as this right here, cubic centimeters. Gallons, quarts, pints, cups, ounces. Okay, and actually we're going to sort of tie these guys together. How the liters relate to quarts and so forth, because we want to be able to maybe have some conceptual idea of what these actually stand for. Pressure, you probably have heard of pressure in terms of pounds per square inch for like your tires, your car. But we also, in chemistry, use something called atmospheres. If you're, if you're a if you're a weather person and you give the weather, you'll hear the weather person may say the barometric pressure is 30. What they're talking about is 30 inches of mercury. You can also have, since inches and millimeters relate, you get millimeters per mercury. Then you could have bar, which different types and so forth. I'm just showing you here that there's different ways of measuring pressure, how they relate to each other. We'll talk about that and which one we tend to use here. So temperature, Fahrenheit, Celsius, and Kelvin. Right. And we'll go more over that. All right. Amount. We said moles and grams. Okay, so what we're gonna do is look at each one of these units and actually compare some of these like liters and quarts and so forth. All right, so let's go over volume first. So volume is measured as length times width times height. It's three-dimensional. Volume doesn't have any negative values. Okay, there's no such thing as negative 3 gallons. The units you'll be something like this. It'll either be something cubed, like inches cubed, centimeters cubed, meters cubed, but it's also going to be in terms of units that don't have any. By looking at it, you don't realize that you're actually looking at volume. We just know it because of what we know, like gallons and liters. And I just want to go over some relationships between some of these. When you hear gallons, inches cubed, liters, centimeters cubed, and all that, and how they all kind of relate to each other. And there's going to be some approximations as I go through this. But so 1 gallon is 3.785 liters, and that's roughly 4 liters. Okay, so so I'd like to think is that if I have a gallon, I roughly have 4 liters. Now it's going to be 4 liters, a little bit more than 1 gallon, but it's a good place to start. Well, 1 quarter of a gallon would be approximately equal to 1 liter. Okay, 1 liter is 1,000 mils. So, and we'll go over when we get as we went over conversions. And you're just gonna have to know this down the road. Is this relationship is 1,000 mils per liter? So if you have 1 quart, you'll have 1 liter, about 1,000 mils. 1 pint, which is half of 1 quart. There's 2 pints per quart. Well, if 1 quart is approximately 1 liter, then 1 pint is approximately 500 mils. And if you look at side of a water bottle, it'll say it'll say this. Okay, it's so it's actually a little bit more. It'd be like 520 mils, or a half a liter. Okay. Well, going on the same relationship, 1 cup, which is half of 1 pint. There's 2 cups per pint. Would be half of 500 or 250 mils. So when I went to Canada a couple years ago, I noticed they had a lot of their measurements. They don't use cups and pints and things like that, but they use mils. But I would often see that they would have like measurement. This is 250 mils, or of a certain liquid, and just because I knew this relationship, I knew that it was approximately a cup. Okay, it's kind of good to know that, since the rest of the world uses mils, but the rest of the world still kind of uses the same units that we use, because we can easily see the relationship between these units. So 1 cup is 250 approximately, and so forth. 1 ounce is approximately equal to 30 mils. There's 8 ounces per cup. Okay, so if you take 1 cup divided by 8 ounces, you would get approximately 30 mils. Okay, so you don't have to know this, but as you look out there in our world, okay, I'm looking right now. I'm looking at a pop bottle, and it says it's 1.25 pints. Okay, so I know that's going to be 500, a little bit more than 500. Okay, with and whatever a quarter is of 500 mils, so 125, so it's about 600 mils. Okay, and on the pop bottle it says 20 fluid ounces, 1.25 pints, or 591 mils. So it's a good relationship, since we are stuck in our world with quarts and gallons and so forth. So 1 centimeter cube is equal to 1 mil. All right. They're basically the same. They're the same unit. Okay. It used to be, when syringes were around, they didn't use mils like they do now. They would say cc's. Okay. So if you got a shot with 2 cc's, it's 2 ml. Cc stands for cubic centimeters. So this right here. All right. 1 liter is approximately equal to 60 cubic inches. The reason why I know this is because when somebody says I have a 3-liter engine, I don't know what that means. Okay, I was raised in the 60s and 70s when everything was in cubic inches. Okay, and now I realize that approximately for every 1 liter there's 60 cubic inches. So if somebody says they have a 3-liter engine, it would be approximately 180 cubic inches. Okay. The cars, these days, the big trucks will have engines that are 7 liters, and big trucks, and I don't know what that means. And then if I multiply that by 60, I get that's about equal to 420 cubic inches, and I know that's a big engine, because muscle cars back in my day would be up around 400 cubic inches. Okay, and another kind of unit, this is the relationship, is 7.5 gallons is equal to 1 cubic foot. Okay, so if you took a ruler, foot long, length times width times height. So here's a foot here, a foot here, and a foot here. You could fit 7.5 gallons inside that, which is actually a lot. Okay. You, for the most part, you may be having to do conversions between these units, and if you do, you'll use our conversion methods that we went over, and you'll be given our pressure. We said that pressure is for force per area. Again, no negative values. Weight is technically force. Weight, like how much I weigh. Weight changes depending on where you are and what planet you're on. Weight is force times the amount of force you apply. Actually, not. Okay. Weight is equal to your mass, times the gravitational pull that's being pulled on you. Now, your mass is the same anywhere in the universe, but because the gravitational pull on different planets and so forth is different, you'll weigh differently, Now, mass times g is acceleration due to gravity, so mass times acceleration we learn as force, and so weight is the same as force. So pounds, the unit pounds, is a force unit. So pounds per square inch is a pressure unit because pounds is a unit of force and square inch. So pounds per square inch. Atmospheric pressure, the amount of pressure that's being pushed down on this from the atmosphere at any given time is approximately 15 pounds per square inch. At sea level, it's 14.7 pounds per square inch. Other units that we talked about, for instance, if you were to talk about inches of mercury, which a weather person will say, like they'll say the pressure is 30.5 inches of mercury. How does that relate to pounds per square inch? Well, there's approximately 30 inches of mercury per 15 pounds per square inch. If you go to Europe, instead of using inches, they would use millimeters. Conversion, so we won't do this here, but the relationship between millimeters and inches is 25.4. So if you multiply 25.4 times 30, you get 760. Torr is another European way of measuring pressure, and basically 1 torr is equal to 1 millimeter of mercury, and so it's the relationship. Bar is what scuba divers use. So they'll say the pressure inside my tank is 1 bar, and that would be 15 pounds per square inch. Physicists will use these things called kilopascals, which is equal to 15 pounds per square inch. And we will be using in chemistry something called atmospheres, where 1 atmosphere is 15 pounds per square inch. Again, if you maybe have to do some conversions when you do these, and you'll be given an exact relationship. These are approximate. So if you hear, like I'll say that some gas has a atmospheric pressure of 3 atmospheres. And you go, I really don't know what that means. Well, that's approximately equal to 45 pounds per square inch. And you may have an idea a little bit of what that's. And that's like the typical mountain bike tire would be 45 pounds per square inch. Amount is going to be moles, 6.02 times 10 to the 23rd. We're not going to deal with this number right now. We'll either just say I have 1 mole, 2 moles, 3 moles, or whatever. We can, like I said, you relate it to mass. There's a relationship between mass and moles, and we'll go over these quantities more when we get to molar gas. But oxygen is O2, nitrogen is N2, and this has a molar mass 32, 28, and air, which is actually mostly oxygen and nitrogen, has a mass of about 30 grams per mole. Okay. And these numbers will be given to you if you need them for right now, so you won't have to do any molar masses. Uh, then here's another relationship. So air has a mass of 1.2 grams per liter, carbon dioxide 1.8 grams per liter, and helium 0.16 grams per liter. Again, you don't have to know these unless I give them to you in a problem. Just want to show you how they relate. Okay, temperature. Temperature. One way to sort of relate it to is the heat density compared to a less heat density standard. So if you have if you have a box that has a lot of heat in it, and then you have a box down here that has less heat in it that we have a number for. Let's say this has 2, and this has twice as much heat in it, then this would have a value of 4. Okay. So what we do is we have some standard heat density, heat per volume, and this is one way to do it. There's other ways to measure that to describe temperature. Then we compare it to some other heat density. And so Celsius and Fahrenheit are the ones that we technically use more, that we use. We use Fahrenheit more than any of them, and the scale of Fahrenheit was developed between 0 to 100 based on 2 numbers. Okay, the guy with what Fahrenheit did, okay, is he said that 0 is the temperature of a system that's made out of salt water that's being frozen. Frozen salt water has a temperature 0. So it's kind of arbitrary. So he just took some salt, threw it in some ice, and found out when it froze, and he called that 0 Fahrenheit. He set the temperature of 100 to body temperature. And now we know what body temperature is 98.6, but his device wasn't as precise as we are now, so that's why it's 100. Okay, why we use that scale. The Celsius scale is a better scale because it doesn't use arbitrary. These are kind of everybody has a different body temperature. This value here is 0 because depending on how much salt you have in your ice. Okay, so instead there's Celsius or centigrade. We use Celsius instead of centigrade. You see it's centigrade. We use 0 to 100, where 0 is the freezing point of water, and 100 is the boiling point of water. And to convert the two, Fahrenheit is equal to 32 plus 1.8 times C. Both of these numbers, Fahrenheit, Celsius, can have negative numbers, but we don't want to have negative numbers, okay, especially when we use the gas laws. So we're going to be using another scale that gets rid of all these negative values. So Kelvin is equal to 273.15 plus Celsius. So, if you're given a Celsius is equal to 20 degrees Celsius, the Kelvin would be 293.15. If you had a negative value of Celsius, like minus 10, Kelvin would still be positive value. And therefore, there is an absolute 0 in the Kelvin scale, while in the Celsius and Fahrenheit, it's a relative 0 based on what we call 0. We won't be using it, but there's also an absolute 0 for the Fahrenheit scale, which is minus 460. Typically what we do is that if you have a 72 degrees Fahrenheit, first thing we would do is convert the Fahrenheit to Celsius, and then the Celsius to Kelvin. Okay. Right. This Rankine is used in like power plants and so forth. Okay, ideal gas law. So, okay, so we will be using those constants for the universal gas law, uh, which is equal to PV over NT. There are two values that we will use at R depending on what we're looking at. If we're looking at R in terms of energy, we'll be using this value, and which we won't be using right now. And what we will be using in our problems right now will be 0.082105 or sometimes 0.0821. Okay, liters per atom, Kelvin minus 1, moles minus 1. If we're going to use this as our unit, we have to make sure our pressure is atmospheres, liters volume, moles, and Kelvin. Okay, now just remember that K to the minus 1 is the same as 1 over K. Sometimes it's easier just to write K to the minus 1 than write it as a fraction. Okay, now one special value that we can get from the ideal gas law is something as standard conditions. So what we have is something called standard conditions, and standard conditions is when you have 0 degrees Celsius or 273 Kelvin and 1 atmosphere, which is normal barometric pressure. And what we want to do is solve for what is the volume of a gas that has 1 mole of gas at standard conditions, and we call it STP. STP stands standard temperature pressure, which is 273 and 1 atmosphere. So STP stands for standard temperature and pressure. So what is the volume of 1 mole of gas at STP? Well, all we do is rearrange the equation for V. Okay, and then we plug everything in. So you get V, 1 mole, times this quantity times the temperature divided by the pressure, and the units cancel out. Atmospheres cancel out, kelvins cancel out, and then you end up with liters. Okay, so what this says is that 1 mole of any gas will have a volume at 22 at STP will have a volume of 22.4 liters. Okay, and finally, we've been dealing with what we call ideal gases. Technically, gases are not ideal. Okay, reality, and so what we have is that we need to add things for ideal gas law. And so we had some corrections for attractions and repulsions. We said that molecules in gas do not attract or repulse, but now they actually do. And we said that they had no volume, but they actually do, and we put that correction volume, and so we get this is a equation for a non-ideal gas, and this is called van der Waals equation. You don't have to use it. If you go into physical chem, you'll be talking about that. And then you can get a crazy equation using something called virial equations, which we're not going to talk about, but it's important in terms of physical chemistry, which we're not going to talk about. And so that's it in terms of units. And next slide will be using these gas laws and the units for problem solving.